Picture a roiling, turbulent ocean of molten rock deep beneath your feet, where heat, motion, and chaos dominate everything. At this stage, atoms are like a frenzied crowd at a concert, bumping, jostling, and constantly colliding, with no fixed positions and no pattern. This is magma, a true molten soup of unstructured elements, where silicate building blocks, metals, and volatiles are all mixed together in a hot, disorganized blur. Now imagine that same chaotic crowd being gently slowed down and brought to attention. As the magma cools, the atomic traffic jams ease, and atoms begin to feel their neighbors, searching for ways to lock into more efficient positions. Little by little, pockets of order emerge. Feldspar, olivine, pyroxene, and quartz start to grow as atoms align into repeating three-dimensional lattices. What began as a shapeless molten mass transforms into a crystalline architecture where each mineral represents a specific solution to the question, how can we pack these atoms most efficiently under these conditions? This journey, from unstructured magma to organized crystal battalions, is the story of igneous rock crystallization. Magmas can freeze in two dramatically different ways, and the result is written into the very texture of the rock. In one scenario, cooling happens so rapidly that atoms never get the chance to organize. They simply stop where they are, like a mob suddenly frozen in place. This produces glass, an amorphous solid with low density, around 560 grains per cubic inch, where atomic positions are random and no true long-range order exists. In the other scenario, cooling is slow and patient. Atoms have time to move, rotate, and negotiate their positions, ultimately stacking themselves into highly ordered, repeating patterns. The result is a dense, crystalline battalion, with grains packed more tightly, about 650 grains per cubic inch, and a rigid, patterned structure. Under pressure, matter is driven toward the most economical arrangement of space, and crystals are nature's answer to that demand for efficiency. So when you look at an igneous rock, you're really seeing the outcome of a timing contest. Did the atoms freeze in a panicked mob, or did they calmly assemble into a disciplined crystalline army? The texture of an igneous rock, whether it's coarse, fine, or something in between, is not an accident. It is controlled by three main architects: cooling rate, viscosity, and volatiles. First, consider cooling rate. Time is the engine of crystal growth. Slow cooling allows atoms to diffuse, meet, and attach to crystal faces, producing coarse-grained, metastable textures where individual minerals are large and easily visible. Rapid cooling, in contrast, creates labile, fine-grained rocks where crystals are tiny or even absent because growth was cut short. Second, viscosity, how resistant the magma is to flow, sets the pace of atomic movement. High-viscosity, silica-rich, acid magmas restrict diffusion, favoring fine-grained textures even if cooling is not extremely fast. Low-viscosity, basic magmas let atoms move more freely, which promotes the growth of larger crystals. Finally, volatiles like water and gas act as a powerful flux. They break silicate chains, reduce viscosity, and can dramatically enhance diffusion. Under volatile-rich conditions, enormous crystals, such as those in pegmatites, can develop, recording a history of enhanced mobility in an otherwise cooling system. Crystals don't simply appear the instant a magma crosses its formal freezing point. To nucleate and grow, atoms must overcome an energy barrier, and that requires a specific amount of undercooling below the equilibrium freezing temperature. At small degrees of undercooling, we enter the metastable region. Crystal growth is possible, but slow, and often requires some form of inoculation, such as the presence of seed crystals or impurities to kickstart nucleation. As undercooling increases, the system can cross into a labile region, where nucleation rates soar and a crystallization explosion occurs, producing many small crystals in a short time. However, if cooling continues too far without sufficient atomic mobility, the magma can become trapped in a high-viscosity, glass-forming state. Here, the mob of atoms becomes too cold to move into ordered positions, and the melt freezes as glass, preserving the disorganized liquid structure. In this way, the path a magma follows through temperature, undercooling, and viscosity determines whether it ends up as a crystalline rock, a glass, or a mixture of both. To grasp how mixtures behave, start with a simple analogy. Pure water freezes at 0 degrees Celsius, while pure salt has its own, much lower freezing point. When you combine them, the mixture does not freeze at the temperature of either pure component. Instead, it solidifies at a lower, shared temperature that represents a compromise between the two. The same principle applies to magmas. In Vesuvius lava, for example, pure lucite would normally freeze around 1420 degrees Celsius. However, the presence of augite as an impurity lowers the effective freezing temperature, keeping the magma liquid until about 1220 degrees Celsius. These impurities depress the thermal ceiling and allow magmas to remain fluid far below the freezing points of their individual minerals. As a result, real magmas are rarely simple. They are complex mixtures whose crystallization temperatures and behaviors are shifted by the presence of other phases, dissolved components, and evolving compositions. In a binary eutectic system, we examine how two components, call them A and B, behave as they cool from a melt. At high temperatures, the system exists entirely as a liquid above the saturation curves of A and B. As temperature drops, the melt composition follows a path down toward the eutectic point, E, which is the lowest temperature at which the mixture can still exist as a liquid. Above this point, one component may crystallize while the other remains partly in the melt. At the eutectic temperature, something special happens. A and B crystallize simultaneously from the remaining liquid. Solid A and solid B form together, interlocking at a constant temperature until all liquid is consumed. Below the eutectic, the system consists only of solid A plus solid B, with no melt remaining. This eutectic behavior produces distinctive textures where the two minerals are intimately intergrown, recording their cooperative solidification at a single fixed temperature. Graphic granite provides a beautiful visual record of eutectic crystallization in action. Under the microscope, you see quartz and orthoclase feldspar interlocking in intricate, script-like patterns, almost like ancient writing carved into stone. This texture forms because quartz and orthoclase crystallized simultaneously at the eutectic point, competing for space and interfering with each other's growth. As they grow together, neither mineral can form perfect, uninterrupted crystals. Instead, they generate a complex, interpenetrating mosaic. In typical graphic granite, the composition might be about 72.5% orthoclase and 27.5% quartz, a ratio that reflects their eutectic proportions. The end result is a rock where the texture itself becomes evidence, almost a signature, of the thermodynamic conditions under which it formed. Plagioclase feldspars are remarkable because they form a continuous solid solution between two end members, calcium-rich anorthite and sodium-rich albite. Instead of separating into distinct minerals, plagioclase crystals can gradually change their internal chemistry as conditions evolve. At high temperatures, calcium-rich compositions crystallize first. As the magma cools, the remaining liquid becomes progressively richer in sodium. Because the crystal remains in contact with the melt, it can react continuously, shifting its composition from calcium-rich to sodium-rich, while retaining the same basic crystal structure. This is recorded in phase diagrams as a plagioclase loop with separate liquidus and solidus curves, between which the crystal and melt co-evolve. The key idea is that these minerals do not simply turn on and off like switches. They evolve with the magma, reshaping their chemistry in response to changing temperature and melt composition, while maintaining a single, coherent crystalline framework. Sometimes cooling is too rapid for plagioclase crystals to fully keep up with the ideal solid solution path. In these cases, the crystal cannot completely make up its mind about its composition, and zoning develops. The core of the crystal forms first at higher temperatures and is richer in calcium, reflecting an anorthite-rich composition. As cooling continues and the surrounding melt becomes more sodium-rich, successive layers added to the outside of the crystal become increasingly albite-rich. The result is a zoned crystal with an anorthite-rich core and albite-rich rims. These outer layers effectively armor the core, sealing it off from further reaction and preserving a detailed, layered record of the changing magmatic chemistry, much like the growth rings in a tree. When we examine these zoned crystals, we are reading a time-stamped archive of the magma's cooling history and its evolving composition. In more complex magmas, we often deal with ternary systems, where three components interact to shape the crystallization path. Here, the composition of the liquid can be visualized as moving across a landscape of temperatures and compositions, with valleys and ridges representing different mineral stability fields. As the magma cools, its composition rolls downhill across this landscape, following paths dictated by thermodynamic laws toward the lowest possible energy configuration. Eventually, the liquid settles into a ternary eutectic point where multiple minerals coexist and crystallize together at the lowest achievable temperature for that system. Just as in binary systems, this eutectic represents the final resting place of the melt's composition, but now the interplay among three minerals creates even richer and more varied textures. The rocks we see at the surface are the solidified snapshots of these journeys across the magmatic terrain. A single parent magma can give rise to many different igneous rocks, and differentiation is the process that makes this possible. One major mechanism is crystal settling. As early formed minerals such as dense olivine crystals grow, they can sink through the less dense melt under the influence of gravity, accumulating at the bottom of the magma chamber. This creates a heavy, mafic cumulate layer, like peridotite or gabbro, while leaving the overlying melt depleted in those components. Another mechanism is filter pressing, which often occurs during tectonic compression. In this process, crystals are squeezed together, and the residual liquid is forced out, migrating away from the crystalline framework. The expelled liquid evolves into more silica-rich, felsic compositions, such as granite or rhyolite, while the remaining crystal-rich mush becomes relatively mafic. By physically separating crystals from melt, these processes break chemical equilibrium and allow one initial magma to birth entirely different rock families. Bowen's reaction series provides a powerful framework for understanding which minerals crystallize from a magma and in what order as it cools. At high temperatures, around 1200 degrees Celsius, minerals like olivine and calcic plagioclase are the first to form, representing mafic compositions rich in iron, magnesium, and calcium. As cooling proceeds, the discontinuous series follows a path of structural change. Olivine reacts with the liquid to form pyroxene, then amphibole, and eventually biotite, each step representing a new crystal structure stabilized at lower temperatures. In parallel, the continuous series tracks the chemical evolution of plagioclase from calcium-rich to sodium-rich compositions as temperature drops. At the lowest temperatures, near 750 degrees Celsius, the remaining liquid crystallizes into potash feldspar, muscovite, and finally quartz, minerals typical of felsic rocks such as granite and rhyolite. This sequence unifies the petrogenesis of igneous rocks by linking mineral assemblages to temperature, composition, and the progressive differentiation of magma. Not all minerals that form early in a magma's history simply persist unchanged to the end. Some minerals are magmatically dead once they crystallize. They remain stable and no longer react significantly with the remaining liquid. Others, however, form reaction pairs, where an early mineral dissolves and is rebuilt into a new structure as conditions change, a process known as incongruent melting. For example, high-temperature olivine can react with the surrounding melt to produce pyroxene. Pyroxene, in turn, can react to produce amphibole as the system evolves. If these reactions go to completion, little evidence of the original mineral remains. But if the transformation is incomplete, we can find corroded olivine cores preserved inside pyroxene crystals, physical proof of the chemical upgrade that was underway but not finished. These reaction textures provide a window into the dynamic, non-equilibrium nature of magmatic systems. Every igneous rock is essentially a frozen moment in an ongoing magmatic reaction. At the high-temperature, chaotic end of the spectrum, mafic rocks such as gabbro and peridotite are dominated by early formed minerals like olivine and pyroxene, often with calcic plagioclase. These rocks record the early stages of Bowen's reaction series, when iron and magnesium-rich minerals crystallize first. As differentiation and cooling progress, intermediate rocks like diorite emerge, containing a balance of mafic and felsic minerals, including amphibole and more evolved plagioclase. At the low-temperature, more ordered end, felsic rocks such as granite and rhyolite crystallize from silica-rich residual magmas, featuring quartz, potash feldspar, muscovite, and sodic plagioclase. Each rock type is a snapshot of a reaction interrupted, and its structure is a direct function of its unique thermal and chemical history. In theory, silica in basic magmas should be consumed early by the formation of silicate minerals. Yet sometimes we find quartz, normally a late felsic mineral, appearing unexpectedly in basic rocks. This phenomenon, often framed in terms of released minerals or doliomorphism, occurs when the normal reaction path is interrupted before silica is fully locked into earlier formed minerals. Imagine a rock as a battlefield of chemical warfare, where minerals are continuously forming, reacting, dissolving, and reforming as temperature and composition change. If the process is halted abruptly, by quenching, eruption, or rapid cooling, the system can't reach its equilibrium endpoint. Silica that would have been incorporated earlier may instead crystallize as free quartz, turning up as an unexpected survivor alongside minerals like orthoclase, pyroxene, and biotite. In this way, the final mineral assemblage preserves the incomplete story of a thermal journey from chaos to order.